Hello, this is Calculus 1, Lecture 7B, Related Rates. My name is Scott Grizzard from the University of South Florida. So last time we talked about logarithmic differentiation, and we skipped ahead in the book, and now we're coming back to talk about related rates. So we skipped ahead a little bit in the future to talk about this application of implicit differentiation. Now we're going to come back and talk about another application of implicit differentiation, that of related rates. So the best way to do it, there's a method to these problems. They're word problems. But what we're going to do is we're just going to kind of break it down. We're just going to do 3 examples. As sangria is pouring from the tap into the cylindrical glass, and the radius of the glass is 1.5 inches. The height of the sangria is increasing in the glass at a rate of 0.5 inches per second. And what I want to know is what's the rate of flow, what's the volume, the rate of flow of the tap. Okay, so that's a kind of typical style related rates problem, and this one's a little simple, so we can get at some of the aspects of these problems. Okay, so let's look at this problem. Let's break it down. Okay, when I do these related rates problems, I need to know a few things. The first thing I really need is a picture. Okay, first thing you always ought to do is a picture. So let's draw a little picture about what's going on here. So I have this glass cylinder, and let's see, it's filling up with the sangria. So the sangria is pouring in, and the height of the sangria is moving, right? As the thing pours, the height level goes up. So here's the height of the sangria, and it's increasing. Now, I've got some volume here that's coming out of the tap going into the thing. So as the volume increases, right, the volume of the sangria increases, the height of the sangria increases. So those are the two kind of things that are related, right? They're related as a rate. The height is increasing so fast, and the volume should be increasing so quickly. Okay. So what I want to do here is I want to sort of list what's going on. Okay. So what's going on here? I've got a radius of 1.5 inches. Now that's never going to change. So I want to ask myself these questions. What is fixed? What moves? And then what drives? Okay. So I've got volume in here, right? I've got the volume of a cylinder. Okay. I know what the formula for that is. So there's a cylindrical glass. I've got this rate of 0.5 inches per second. And I want to know the rate of flow and volume of the tap. Okay. So I have a relationship immediately. That's the volume. The volume of a cylinder equals pi r squared. So that's the area of the circle on the bottom and the top. And then I'm going to take that area, I'm going to multiply it by the height. And that gives me the volume of a cylinder. Now I've got some variables here. I've got the volume of the sangria in the glass. Okay, so from my relationship that I immediately identified, I've got these kind of variables going on, right? I've got some volume in the glass. And remember, I want to ask what's fixed, what moves, and what drives. The volume is moving. It's changing as the problem goes. So when I hit play on the video, the volume is increasing in the glass. Likewise, so is the height. So both of these things, the height. So both of these things move. And what's going on there when I hit play? Well, there's this variable that I'm not talking about right here in this relationship, but that's time. Time goes forward and it drives the problem. In this case, it is in seconds, and this is the driver. Now, I have the radius of the glass, but the radius of the glass doesn't change, right? It's a solid piece of glass. It's not liquid, molten liquid changing the radius, right? It's just the radius of the glass is fixed. So I'm going to say that that's fixed. Now, what I'm looking at is a dynamic system. And what I want to do is I want to say something about that dynamic system. In fact, what is it the thing I want? I want here, right, the rate of flow. So what I want is dV over dt. I want to know the change in the volume with respect to time. So again, I'm going to have to take a derivative of this thing, and I need to identify the moving parts, because if something is moving with time, I can't substitute in data for it. But if something's fixed, I can. Okay? So what have I done? Well, I've identified the various pieces of information here. Next, what I'm going to do is I'm going to sub in, again, I'm looking at a system that moves. So anything that moves, I can't change. Anything that moves, I can't sub in data. Okay, so if it moves, I can't sub in any data. But anything that's fixed, I can sub in. So here's my relationship. And I've got, these things are moving, moving, fixed, moving. So the R can go in right away. The V and the T, nothing can happen there, but the R can go in right away. I should put down my other variables here. Now I'm going to sub in my fixed data. Again, it's very important that you sub in nothing that moves. So the radius didn't move, so I'm going to sub that in. Now that I've subbed in the fixed data, and notice what just happened there. Because I'm doing, my derivative just became simple. I don't have a product rule here anymore, do I? I just have a constant multiple. Pi times 1.5 squared, that's all a constant. Okay. So now what I'm going to do is take the derivative of everything in terms of the driver. The driver in this case being time. Okay. And then I'm going to snub in any snapshot data I have. Okay, so this is data that happens at a particular time. It's usually moving, but when I hit pause, it stops. So you can think of this as pause data. Okay, this is data that's only fixed when I pause. Okay, so that's my pause data, right? And there I get an answer, right? It's approximately that, and it should be in, this should be in inches cubed per second. Now what I'm going to do is I'm going to double check my units. So my units on dV over dt, I said were inches cubed per second. My pi here is just a constant. I had inches. My radius is in inches, but it's squared. And then my height was in inches per second. So the units all cancel. And I am good. So I just want to check my units. All right. Then what I want to do is I want to write my final answer. And so these problems, there is an issue with these problems in that it'll say something's increasing and then ask if it's decreasing. So that might mean you need a negative answer, or you might have a positive answer with a positive answer and all of that. And there's all this confusion. So what you want to do is you want to impose an interpretation on the problem. Okay. So you say what you mean. And that's very important, because that not only saves you points, it saves you confusion in the real world too. So what you do is you give yourself a context. So I said the sangria is flowing from the tap at a rate of 3.5325 inches cubed per second. So what I have done is I've imposed an interpretation. I've said what I mean for it to say, right? This is my problem. This is my solution, and I'm telling you what I mean by that solution. Okay, so this was what happened here. I drew a picture. I identified the variables and units for those variables. Chart, not a bad idea. I identified what moves, what doesn't move, and what drives. Now, usually the driver will be time, though not always. We'll do one where it's not. So we'll do one with depth and pressure where time is not the driver. But in economics, you a lot of times see time is not the driver. But usually what's driving the problem is time, right? Things are happening in time. I want to identify some relationship between the variables. Here, my relationship was the volume of the cylinder. Okay. I substituted in all the static, non-moving, and only non-moving things, okay? So that will make my math easier, but that goes in first. Then I differentiate implicitly in terms of the driving variable. I substitute any of my snapshot or pause data, then I solve, I check that my units make sense, and then I state in my own words what the answer means. Okay, so that's sort of the method for solving these problems. So in the ocean, pressure, I'm going to measure it in bar. You can measure it in atmospheres. It actually comes out to be about the same thing. Increases in depth, which I'm measuring by meters. And the rate of the change is 1/10 of a bar per meter. Okay, so every 10 meters I go down, I get another atmosphere of pressure, another bar of pressure. At 40 meters of depth, the pressure is going to be 5 bar. So here's what I wrote. Now, holding temperature constant, Boyle's law states that volume in liters of a sample of gas under pressure satisfies the equation PV equals C, where C is some constant.
Boyle's law describes the behavior of gases under varying amounts of atmospheric pressure. It states that if a diver holds his breath at 100 feet, continues holding while rising to 10 feet, then the gases in his lungs increase 4 times.
Okay, so as pressure goes, as you increase the pressure, the volume is going to go down. So as you increase in depth, a bubble is going to shrink. Or as you decrease in depth, as you come up, the air in your lungs will expand, which is why you shouldn't hold your breath. Now, number one rule of scuba diving, never ever hold your breath.
Now, why is this important to a diver? Forget to exhale on the way up and your lungs explode.
Assuming that temperature is constant, and suppose that diver Dave exhales a bubble of air, which starts rising to the surface. Now, I don't know how deep he was when he rose. I don't care how quickly the bubble is rising. My question is, when the bubble reaches 40 meters of depth, okay, and its volume is 1 liter, what is the rate that the volume is what is the rate of volume that the bubble is changing with respect to depth? Not time. I don't care about time. My question is, what's the marginal change in volume with respect to depth at 40 meters of depth if the bubble's already 1 liter in size? So now I've got some data going on here. So let's ask the question again. We wanted to ask this question. What's fixed? What moves? What drives? Okay. So let's see. What have I got here? I've got, let's throw out some variables here. I've got pressure, volume. I've got some C constant. Okay. So I've got some pressure here, some volume. These things are going to change. So what's driving this is depth. Okay. That's the thing on the bottom. What rate is the volume of the bubble changing with respect to depth? So this is the driver. Okay. The gas constant is fixed because it's, hence the name, gas constant. The volume, well, the volume here moves, right? It changes. As the bubble goes up, the volume is getting larger. And the pressure is going to change with depth, right? So as depth decreases, pressure decreases. As depth increases, pressure increases. What's fixed here? The only thing that's fixed here is the gas constant. Notice I actually have data, right? I've got some data. I've got 40 meters of depth and I've got 1 liter, but that's not fixed. Remember, before, the radius of the glass was fixed. It didn't change while the problem. I hit play on that little video and the radius of the glass wasn't changing. But here, as the problem moves, right, as the depth changes, all of these things are going to change. That's snapshot data. That's pause data. I'm going to write that over here, and I'm just going to say pause data. I'm going to write that right over here. This is data I cannot sub in yet. Okay, so this data is pause data. I can't sub it in yet. So there's nothing really fixed. What's the relationship here? The relationship is PV equals C. The gas constant is fixed, but I don't know what it is. Okay, so, and then the other things I want to solve. I have dV with respect to depth. Okay, so I've got some, changes here that's going on here. And then I've got a relationship. Well, my relationship is PV equals C. Okay, so what I need here is dP over dd. Well, let's do the differentiation here. So I'm going to take the derivative of everything with respect to depth. Okay, because that's my driver here. So here I'm going to have a product rule. Okay, and here this is going to be a constant, and that's nice. And that's why I wanted to leave this. I don't want to multiply and separate this because I really like the fact that that's a constant over by itself. Because what happens to constants? Right? They go bye-bye when we take derivatives, if they're all by themselves. So we just want to leave that one by himself. Right? He's going to become 0, and we like that. This is going to have a product rule attached. Okay, so now I've got the derivative of p with respect to d plus times v plus, well, that's what I wanted, right? So what do I have here? I know that the pressure changes with depth. I actually do know that. That was way up here. That was 1/10 of a bar per meter. The volume, so now I sub in my snapshot data. And notice I waited until after I took the derivative, okay? Remember, everything's moving, and now I hit pause, but I don't sub in my data into the stuff that's moving before I take my derivative. I have to take my derivative first. Now I sub in the pause data. So now I check to make sure that these things confirm. Notice that these things are added. I bet that one of these is going to be negative when I'm done. But I kind of did the relationship at the same time here. So when we do this over, notice this is bars per meter. So when I sub one of these over, I'll get the right units. And that's just what I wanted to check. Okay, and then I divide both sides by the 5. So I get -1 over 50 liters per meter. So I've got liters per meter, and don't try to like convert liters to cubic meters or something like that. Okay, don't do it. This is a meter in depth, which is something different than a liter of gas, right? So it's not a square meter or something like that of gas. That makes no sense. Okay, it's liters per meter of depth. Okay, and my units checked, right? I'm going to have, when I subtract one from this side, the 2 units are going to match and cancel. I want to make sure that's true. Okay, so there's my solution for the number, right? That's what WebAssign would want. But now, notice that this is negative, and that's a little confusing. So I am going to impose my own interpretation on the problem. And so what I'm going to say is this. I'm going to say that the volume, because the bubble's going up, right? So the volume of the bubble is increasing. So notice what I did. I imposed my interpretation on the problem. I said the volume of the bubble is increasing at a rate of 1 over 50 liters per meter of depth as the bubble rises when the bubble is at 40 meters of depth. I could have also said the bubble is decreasing in size as the depth increases, but the bubble's going up, not down. So I said it this way. You can say it how you want to as long as it's a valid interpretation of the problem. Okay? And I imposed it. I didn't deal with this -150 because look, the thing asks, at what rate is the volume of the bubble changing with respect to depth? Is that negative? Is that positive? I mean, the depth's decreasing. I don't know. So, if all you do is write 1 over 50 or -1 over 50, what does that mean? Well, I said what it means. I said it's the volume of the bubble is going up and the depth is going down, right? I said the bubble was rising. So I imposed an interpretation on the problem. Okay, let's do one more example. Here, I've got a baseball. I've got the runner on first. She's going to try to steal second, okay?
You look real sharp, but it's hard to steal second base with your shoe untied.
So what I want to know is what's the change in the distance between the catcher and the runner? The runner's running this way. What's the change in the distance between the catcher and the runner as the runner makes his way to second base? Okay? Let me put it a different way here, okay? As the pitcher begins his motion, the runner's stealing. The runner on first makes a dash for second base, and he's going to run at a speed of 24 feet per second. He's going to be halfway. Now, a baseball diamond is 90 feet from here to there, okay? So it's 90 feet from first to second.
Going somewhere, meet? About 90 feet.
And so the base stealing runner is halfway when the ball hits the catcher's mitt. Now, my question is, at what rate is the runner's distance from home plate increasing at that matter? So I know that this side right here, the runner is going to be here now, but the runner's moving.
Hayes, go!
Now, there's some distance between the runner and first, the runner and second, and the runner and home. Well, if I look at this, I'm going to have a triangle. And these triangle problems can be a little tricky. The key is figuring out how to set them up. So here, I've got some distance, right? This is the distance from the first base to the runner. This right here is the distance between home plate and the runner. And the runner is moving this way at 24 feet per second. Now, this would make a nice little Pythagorean triangle here, right? This right here, I know that this is 90 feet. I'm going to call that B. Here, I've got a right triangle. So I'll call that A. I'm going to call that C. So what are the variables? What's going on here? Well, I know that time's the thing that's driving. So I'm just going to write that, right? The runner is running at 24 feet per second. Time is driving this thing. Okay, we're going to write that down first. So T, time, it's feet per second. I'm sorry, it's seconds. It's our driver. Okay, now, this right here, B is the distance from home to first. And it's measured in feet, and it is fixed, right? The distance from home to first is 90 feet. Not 89 feet, not, something different. And we're not playing softball here. And the base is not moving. We're not playing stickball where, the first baseman starts to kick the base when it's a close call. No. The base isn't moving, right? It's nicely fixed into the clay. Okay, what is moving here? Well, the distance between first and the runner. Well, that's also in feet, but that moves. And now I'm going to have some rates up here. Let's throw on our rates. Okay, and this thing's fixed, so I'm going to sub that in. Let's write out our snapshot data. So when I hit pause, A is going to be 45 feet. C is unknown. B here is 90 feet, but that's actually fixed. That's not snapshot data. So I'm going to stick that over here because I'm going to sub that in right away. And let's see. Do I have anything else that I'm going to need for this thing? Nope. And then my rates are dA over dt. Okay. So I don't know what C is going to be, but I know that there's some snapshot data going on. Okay. So my relationship here is the old Pythagorean theorem. And because B is fixed, I'm going to sub that in right away. Okay, so it just goes in. And that's going to be lovely, because when I take this derivative in terms of t, 90 is just going to go bye-bye. Okay, so now I take the derivative with respect to t. Now, notice here that nothing is in terms of A and C. I'm going to have a chain rule here. Because I've got a t and an a squared. No, I need to do it with the derivative with respect to a. So what I'm going to have here. Okay, so now I have the change in a squared with respect to a times the change in a with respect to t plus 0. I did the sum rule here, but I didn't write it out. And then I did the derivative with respect to c of c squared times dc over dt. Because the change in c squared caused by c times the change in c caused by t. So for my snapshot data, I actually need two pieces here. I actually need A and C. And what I have is just C. So I'm going to have to solve for the snapshot data, which means that I need to solve for my needed snapshot data. I'm going to do that right here. Or my pause data. I keep saying I'm going to call it pause data, and then I never do. Okay, so my snapshot data. So I've got A equals, so my relationship here is A squared plus, and I need to solve for C. So A equals 45, so I'm going to have 45 squared plus 90 squared equals C squared. Now, before I yank out my calculator and go, let's see what this is, let's look at this, okay? I've got 45 squared plus 90 squared, and then I know that I'm going to be taking a square root of everything. And that, hold on for a minute, okay? So before we yank out the calculator and square 45 and then square 90 and add them together, I've got a 45. This right here is 45 times 45. Now 90 is 2 times 45. So this is 90 times 90. That means that this is 2 times 2 times 45 times 45. Right? I'm going to have each one of these 90s is 2 times 45. So when I square it, I'm going to have two 2's, and then I'm going to have a 45 times a 45. And what I'm going to end up doing here is squaring these. Okay? So instead of just yanking out the calculator, let's do something a little bit intelligent. Let's do something a little bit wise. And let's just say, okay, what I've got here is a 45 squared plus 4 45 squared. And now I'm going to group these, right? That's 5 42 squares. Right? It's 45 squared plus 4 45 squareds. That's 5 45 squareds. Now I take the square root. I'm going to get root 5. So I'm going to get 45 root 5 equals C. So I could have just popped it into my calculator and gotten a log decimal. But if you look at this for a moment, you see that 90 squared and 45 squared. Wait a minute. Those things have prime factors in common. In fact, this right here is 2 times 45. So step back and look at it. Sometimes you don't need your calculator. And you can come out with a nice answer like that. Okay, so now that I have my data, I'm going to merge this information here with this information here. So I'm going to put everything together, and look what happens. I have 2 times A. Well, my A, and my data here was square root 5. So I'm going to have 2 times A, and A is 45 feet, times dA over dt equals 2 times C times dC over dt, which is the thing I want. And my units match. So that's just a little check for myself. So this is going to become my answer. Okay, so now what's going to happen? The 2's are going to cancel, and look at that. The 45's cancel. I love you. I love it when that happens. 2 times 45 times 24 equals 2 times... Look at all those beautiful things that cancel. That goes, that goes. These both become 1s. The 45's cancel. They both become 1s. And what I'm left with is 24 over the square root of 5. Okay. So, and again, I am going to impose my interpretation. Okay, so I've imposed my interpretation. Now, a decimal answer would have worked fine there. If you're uncomfortable with that little bit of slick algebra, that's okay.
Here's the throw!
All right, so we've done 3 examples. Let's go over a definition that we're going to be needing. And we've actually seen this for a while, okay? What I'm going to say is I'm going to let f be some function, some x value, okay? So I need to define what linearization means, because we need this for next week, for the time I see you after this lecture. So let f be a function. We're just going to define linearization. F be a function, A is some number in the x space, and let f prime of A exist. The linearization of f at x equals A is the following function. L sub f A, right? So this is the linearization of f at A of x equals f of A plus f prime of A times x minus A, right? So the subscripts are often admitted, and you'll often see one of them admitted, especially when I've been doing this, like when I've been doing the linearizations on Desmos. You can go back to previous lectures and see this. You'll see me write L sub A, but I knew what the F was, so I didn't write the F subscript.
Cross him off then.
Okay, so that's what I have for you today. Have a good rest of your day.
Don't worry, nobody's listening anyway.